My dear students, in my previous video, I have defined various types of vectors and also triangle law of vector addition and parallelogram law of vector addition we have seen. Now, continuation of that vector addition, position vector of a point position vector of a point is given. Suppose A is a point with respect to the origin O, position vector of the point A is A vector and position vector of the point B is B vector. Position vector of the point B is B vector. Now, what is the vector AB? By using triangle law of vector addition, we know that let A and B be any 2 points in a space with respect to the origin O. With respect to the origin O, the position vectors of the point A and B, the position vectors of the points A and B are OA and OB respectively. See, you should write an arrow symbol above that representation of the vector. You should always give an arrow mark for a vector notation. It should be given by an arrow mark. Unless otherwise, if you just simply write AB, it is not a vector, it is a scalar. It represents the distance AB. Therefore, you have to use an arrow mark for vector notation. Now, by triangle law of vector addition, by triangle law, OA vector plus AB vector equal to common point A, OA plus AB. Through the common point A, you start with A and end with B. Therefore, OA plus AB is OB, you know, by triangle law. From this, AB vector equal to, from this expression AB vector equal to OB vector minus this OA, if you bring it to the right hand side, it's minus OA. So AB vector is OB vector minus OA vector, that is position vector of B minus PV means position vector of A. Position vector of B minus position vector of A. Position vector of B, you know, B vector, small b vector, minus position vector of A is A vector. So AB vector is OB minus OA, or position vector of B minus position vector of A. This is our representation of AB vector by using triangle law. Suppose BA, reverse direction, if you find BA vector is position vector of A minus position vector of B. Position vector of A is OA minus OB. Position vector of A minus position vector of B, that is A minus B. A vector minus B vector. Position vector of A is A minus B. See, BA is OA minus OB. So AB is OB minus OA and reverse direction BA is OA minus OB. Okay. This is a representation of a vector by using the position vectors. Okay. One more idea. Suppose this is the origin O and position vector of the point P is OP. Position vector of the point Q is OQ. I want PQ vector by triangle law. PQ vector equal to OQ minus OP. by the above result. This is OQ, position vector of Q minus position vector of P, OQ minus 1. Similarly, QP vector is position vector of P minus position vector of Q, that is OP minus 1. That is OP minus 1. Like that, vector representation can be represented using the position vectors. Next idea is multiplication of a vector by a scalar. Multiplication of a vector by a scalar. Or scalar multiplication of a vector. Multiplication of a vector by a scalar. Multiplication of a vector by a scalar. Suppose AB is given by the vector A vector. AB is extended to C twice. This is A. Again it is extended by the same direction of length A. So this is nothing but this is 2A vector. So multiplication vector A by a scalar 2. 2 times of A is 2A vector. This is the scalar multiplication of a vector. 2 is a scalar. This means that A is the vector A is twice that of the vector. 2A is scalar multiplication of vector A by 2. Suppose if you reverse the direction, this is A minus A. If you reverse this direction in the opposite way, this is minus 2A. This is minus 2A. So scalar multiplication in the opposite direction, minus 2 is also a scalar. You can multiply a vector by a scalar whether the scalar is positive or negative. It is minus 2. Like that, scalar multiplication is explained. Or suppose this is AB is of A vector. AC is another vector. It is called half of A vector. AC is half of A vector. Here also we are multiplying the vector by a scalar 1 by half of A. Suppose if you change the direction, it is minus half A. Like that, scalar multiplication is explained. Now, components of a vector in 3-dimensional coordinate space. Now we are going to define an important area. Representation of a vector in a 3-dimensional coordinate space. Components of a vector. Components of a vector or representation of vector in a 3-dimensional coordinate plane space. Components of vector in 3-dimensional coordinate space. See, you see the corner of a wall. Any any corner of a wall or the wall of a corner consisting of three axes. In two dimension we have find only x-axis, y-axis only. In two dimension we have find two axes, x-axis and y-axis only. Or otherwise, if you like, if you consider this is origin, two-dimensional plane consisting of two coordinates only. Therefore, any point in this coordinate axis you can represent by x comma y. This is x and this is y. T x comma y is any point. It can be represented in two-dimensional plane. Whereas in the three-dimension, you can define only in space. See, x-axis, y-axis, z-axis. Corner of a wall is always consisting of three axes. For example, you can see this is x-axis and this is y-axis. And one more axis you have, mutually perpendicular axis they are. This is your z-axis. Like that. These are three mutually perpendicular axes. X-axis, y-axis, z-axis. These are three mutually perpendicular axes represented by the corner of a wall. This can be represented only in space. A three-dimensional coordinate system cannot be drawn in the two-dimensional board. It is represented only in the space. That's why in the two-dimension you can draw a circle. This is two-dimensional representation diagram, circle. Whereas the same, it is globe. In the space it is become a globe. We cannot draw globe in the blackboard. It consisting of three-dimensional shape. That's why three-dimensional coordinate system consisting of three coordinate axes, x, y and z. In that axis system, we are going to define a vector. That's our idea. See, OX. See, this is you consider as origin. This third coordinate you have to drawn like this. In the plane you cannot draw three mutually perpendicular axes in the plane. One is x-axis, another is y-axis. Third one is z-axis. In this direction you cannot draw. That's why you assume that this line actually projected outward from the backboard. Okay, that is your x-axis. This is your y-axis and this is the z-axis. This is the three-dimensional coordinate system. OX, OY, OZ. OX, OY and OZ are three mutually perpendicular axes in space in the three-dimensional coordinate system. OX, OY and OZ are three mutually perpendicular coordinate axes in space. And O is the origin and O is the origin. Let's I cap, J cap and K cap. Cap notation is, I already told you, the cap notation represents the unit vector. I have given a definition for unit vector. Unit vector is a vector whose magnitude is 1 and it can be represented by the cap notation. We have seen in the definition of unit vector. So I cap and J cap and K cap are the three unit vectors. Three unit vectors acting along OX, OY and OZ respectively. So I is a unit vector in the x-axis, I cap. J is the unit vector acting along y-axis and k is the unit vector acting along the z-axis. So any point P x comma y comma z is any point. This is x coordinate along the x-axis, y coordinate along the y-axis, z coordinate along the z-axis. P x y z is any point in the space whose position vector from the origin O is OP. It is defined by R vector. Let P x comma y comma z be any point in the space its position vector is the position vector of the point P is OP vector. It is defined by R vector. It can be expressed as x into I vector in the x-axis, xi vector plus yj vector plus zk. This is the representation of a vector in its component, which is component x, y, z are the components of OP vector in x-axis, y-axis and z-axis. So R vector is xi plus yj plus yj plus zk. Sorry. R vector is xi plus yj plus zk. Is a representation of a vector in its components. Okay, I, j, k are the unit vectors acting on the coordinate system. Now suppose the OP vector makes an angle alpha with the x-axis, beta with the y-axis, and OP vector is making alpha with the angle x-axis, beta with the y-axis, and the OP vector makes an angle gamma with the z-axis. Now alpha, beta and gamma are the angles made by the OP vector with the axis OX, OY and OZ respectively. Let alpha, beta and gamma are the angles made by the vector OP, angles made by the vector OP with the coordinate axis OX, OY and OZ respectively. Let alpha, beta and gamma are the angles made by the vector OP with the coordinate axis OX, OY and OZ respectively. Therefore, R vector is xi plus yj plus zk. See, distance between modulus of R vector means OP vector is modulus of R vector. This is nothing but R vector. This is nothing but the distance between OP and O. That is, this is origin 0, 0, 0. So x minus 0 whole square plus y minus 0 whole square plus z minus 0 whole square, square root of distance formula, distance between OP. Modulus of OP is distance between OP. That is root of x minus 0 whole square, that is x square, y minus 0 whole square, is y square, z minus 0 whole square, z square. This is the modulus of the vector OP. R vector modulus is, this is defined by small r, which is equal to root of x square plus y square plus z square. This is nothing but the distance between O and P by using distance formula, root of x minus 0 whole square plus y minus 0 whole square plus z minus 0 whole square, otherwise root of x square plus y square plus z square. This is the magnitude of the vector OPR. Now, one more thing. Suppose the angle, you draw a perpendicular line PQ to the y-axis. From the point P to the y-axis, PQ is the perpendicular line drawn from the point P to the y-axis, and beta. What is cos beta? Cos beta is the angle adjacent side by hypotenuse. Adjacent is y. By hypotenuse is r. Modulus of r. Distance is OP is mod of r. Distance cos beta. By result only you can first you write cos beta equal to adjacent OQ by hypotenuse OP. Adjacent OQ is Y. Hypotenuse OP. OP is small r or r small r. Okay. See, you don't get confused this. This OP is distance of the modulus of vector R. Distance of the modulus of vector R. OP is mod of OP equal to distance of the vector mod of R. That is given by Y by R or Y by mod R, whatever it may be. You write here cos beta equal to Y by mod R, modulus of R I mean. Y by modulus of R or simply R. Similarly, cos alpha adjacent side x by modulus of R. Similarly, we can represent cos alpha equal to x by modulus of R, and cos gamma equal to Z by modulus of R. So cos alpha is x by modulus of R, cos beta is y by modulus of R, and Z beta is cos gamma is Z by modulus of R. Therefore, from this idea, adjacent by hypotenuse, for this you can project this x-axis like that. You will get beta is diagonal by the vector OP with the x-axis, that is x by modulus of R you will get. Similarly, if you draw Z, it's a perpendicular line. Adjacent for alpha is a gamma. For that, for this also we can write as these are Z by modulus of R. Z is the adjacent side of Y axis. Okay. So this cos alpha, cos beta, and cos gamma are the directions cosines or direction cosines of vector R or vector O. Simply they are called DCs of vector R. So cos alpha, cos beta, cos gamma are the direction cosines of the vector R. And all vector you know, xi plus yj plus zk. These x, y, z are called direction ratios of the vector R. These x, y and z are the direction ratios of vector R. So any vector x, components x, y, z are called direction ratios, and the cosine angles of the vector cos alpha, cos beta, cos gamma are the direction cosines of the vector. I will stop here using these two ideas. I will stop here and I will continue the same in the next video. Thank you.